Welcome to AI Paper Slop. You drop the paper from pixels to words towards native one vision models at scale into our queue. And if you are actively building or training vision language models, this is a structural shift you need to process immediately.
Yeah, it really is a massive paradigm shift.
So let's jump straight in. Here's the core 60-second insight for you. The industry status quo right now is to build modular VLMs by stitching a frozen visual encoder, like CLIP, to an LLM using an adapter.
Right, the standard pipeline.
Exactly. But that modular pipeline intrinsically destroys fine-grained spatial and temporal details before the reasoning phase even begins. So this paper introduces NEOOV.
Which stands for Native One Vision.
Right. It is an encoder-free, monolithic foundation model. It processes raw pixels and words natively, end-to-end, in a single sequence.
And it does that without a massive vision transformer.
Exactly. By utilizing a unified serialization scheme and a decoupled spatial-temporal, or THW, attention mechanism, it naturally handles single images, multi-image documents, and video inputs.
All in the same architecture.
Yeah. The major takeaway is that NEOOV doesn't just match top modular models like Quinn 3VL and Intern VL 3.5, it absolutely dominates in spatial intelligence benchmarks.
Which is huge.
It proves that native one-vision architectures are highly competitive at scale without any external compression.
And, to understand exactly why this architecture achieves those spatial benchmarks, we really have to tear down the bottleneck of the modular status quo.
The exact bottleneck you've likely been wrestling with in your own VLM builds.
Right, because the ML community has been heavily reliant on this encode then project standard.
Yeah.
I mean, architectures like Elavi or the Quinn VL series you might be deploying, they follow a very rigid pipeline.
It's always the same setup.
Yeah. You take a pre-trained vision encoder, you compress the image into a set of dense embeddings, push that through a lightweight MLP adapter to bridge the dimensional gap, and then finally feed it into the LLM.
And you're basically forced into a system of compromises there, right? Because of fundamental constraints in flexibility, efficiency, and scalability.
Yes, exactly. Let's look at flexibility first. The current paradigm enforces this false dichotomy between spatial and temporal processing.
Like having to choose your poison.
Yeah, if you use an image encoder, it has a heavy inductive bias towards static, frame-level representations. So it fails completely at long-horizon spatiotemporal reasoning.
But if you pivot to a video encoder, you have the opposite problem.
Right. It overemphasizes temporal dynamics. And then its performance severely degrades when generalizing back to static single images or like interleaved multi-image documents.
And the efficiency penalty of that separation is just brutal, especially when you look at the KV caching dynamics.
Oh, KV cache is a nightmare in modular setups.
Right. When you decouple the vision and language modules, extending those traditional visual encoders to handle high-resolution inputs or long-duration streaming video, the compute costs scale prohibitively.
Because every single frame of a video has to pass through a massive vision transformer.
Yes, and the visual tokens generated are incredibly dense. Because the encoder operates independently of the LLM's core attention mechanism, storing these keys and values across long temporal windows just exhausts your VRAM rapidly.
Standard KV caching optimizations that were designed for autoregressive text simply don't translate efficiently to these redundant, dense visual embeddings.
Not at all. And then there is the scalability nightmare. Modularity means you are constantly balancing the parameter capacity of the vision encoder against the language model.
Which is really tricky to train.
It is. If you have a 6 billion parameter encoder fighting a 70 billion parameter LLM, their gradients are essentially tugging the adapter in different directions during training.
Yeah, but honestly, the biggest tragedy of the modular pipeline is semantic filtering.
Oh, this is the worst part.
Pre-trained vision encoders like CLIP or SIGLIP, they are optimized purely for image-text alignment. They're just hunting for high-level semantics. So by design, they actively discard local geometry, texture, fine spatial structures, and they do this before the LLM even gets to look at the data.
It is exactly like taking a massive uncompressed raw photograph, running it through a highly aggressive JPEG compression algorithm tuned only to identify dogs and cats.
Yes.
And then asking the language model to count the exact number of leaves on a tree in the background. You've already mathematically destroyed the data it needs to answer the prompt.
That's a perfect analogy. The language model is forced to hallucinate geometric reasoning over semantically filtered representations rather than native visual signals.
It's just guessing at that point.
Exactly. When your model tries to track a moving object across frames, that cross-frame interaction is being mediated through those heavily compressed CLIP features instead of native spatial correspondences.
Which fundamentally bottlenecks your pixel-level consistency.
Right. So the researchers behind NEO approached this by completely stripping out the massive vision transformer.
They just threw it away.
Gone. To get the pixels into the network natively, they introduce a remarkably lightweight patch embedding layer.
Right, and it's basically just two convolutional layers with a GEOU activation function in between, isn't it?
Yeah, that's literally it. The first conv layer extracts features with a stride of 16, and the second aggregates those local features with a stride of 2.
So the result is just one visual token for every 32 by 32 pixel region of the image.
Exactly. Instead of relying on a deep, computationally heavy encoder to interpret the semantics of the image, this convolution setup is performing minimal, localized geometric aggregation.
Just enough to get the pixels into a token format.
Right. And once the model has those raw visual tokens, it wraps them in explicit image and /image text tags.
Oh, like standard HTML style tag.
Yep. And from there, they're concatenated directly with the standard text tokens generated by the LLM tokenizer.
So you end up with a single unified backbone processing both text and raw spatial data simultaneously.
Yeah, the serialization scheme they use to manage the different modalities is actually very clean.
How does it handle interleaved inputs?
So if you pass a single image, it drops the visual segment exactly at the image position in the sequence. If you pass an interleaved document with multiple images, each image gets its own independent visual segment dropped chronologically.
And it adapts to its own spatial size, right? It's not forced into a fixed token budget.
Exactly. And for video, they sample a specific number of frames, say F frames, and treat each frame as an independent image unit.
But they need to track time somehow.
They do. So they prepend an explicit text timestamp. The autoregressive sequence literally reads as, 81: image tag, visual tokens, end image tag, then 2, and so on.
That global prefix encoding the video duration, paired with explicit text timestamps, allows temporal information to be intrinsically mapped alongside the visual data.
The network doesn't even need a dedicated temporal module.
Because video understanding naturally emerges within the exact same framework as reading a multi-image PDF. But, okay, hold on. Let's look at the math here, because this is the exact point where anyone training these models is going to raise a massive technical red flag.
Sequence length.
The sequence length. If we strip out the heavy encoder and we are literally dumping raw 32 by 32 patch tokens straight into an autoregressive LLM, the sequence length is going to explode.
Oh, absolutely.
A single 4096 by 4096 image produces over 16,000 tokens.
It's massive.
If you push a 128 frame video into this architecture, standard attention mechanisms, which scale quadratically, should completely melt the GPUs.
Yeah, you dome immediately.
So how does this architecture organize a sequence of that magnitude without triggering an out-of-memory error?
Okay, so the solution to that sequence explosion is really the core technical innovation of the paper. It's native spatial temporal attention paired with native rope.
Rope B being the rotary position embedding.
Right. They had to completely redesign the LLM's attention mechanism to handle uncompressed spatial sequences. Let's start with native rope-E.
Because normally in standard text models, rope-E is strictly one-dimensional because text is sequential.
Exactly. But NEO introduces a 3D indexing system, formatted as THW, temporal, height, and width.
Wait, so what happens to the text tokens?
Text tokens only receive a temporal index. Their height and width values are strictly 0.
Okay.
But image tokens receive their sequential temporal index plus their exact spatial coordinates.
So mathematically, the model knows exactly where a patch sits, not just in the sequence of the prompt, but its precise XY physical location within its specific image frame.
Exactly. And that 3D coordinate system feeds directly into their decoupled THW attention mechanism.
How does it break down?
They preserve the LLM's original attention head dimension exclusively for temporal, or T modeling.
Right.
But then they expand the architecture by adding extra dedicated head dimensions specifically for height, the H, and width, the W.
Oh, wow. So when the model calculates the correlation between a query and a key token, it doesn't compute one massive attention score.
No, it computes the temporal interaction, the height interaction, and the width interaction independently.
Yeah.
And then sums them.
That makes so much sense. The T branch handles textual order, cross-image relations, and cross-frame dependencies, while the H&W branches are purely focused on mapping 2D spatial structures within individual frames.
Yeah, which brings us directly to the masking trick that actually prevents the quadratic complexity from blowing up the compute.
Because they still have to run attention over tens of thousands of tokens.
Right. So they apply a highly structured attention mask to this decoupled mechanism. Inside a single image or a single video frame, tokens are allowed to attend bidirectionally.
Which is crucial, right? Because spatial geometry is non-directional.
Exactly. A pixel needs context from the pixels above, below, left, and right to actually understand an object's shape. This creates dense, localized spatial interaction.
But what about across different images?
That's the trick. Across different images, across different video frames, and across text, the attention mask enforces strictly causal autoregressive behavior.
Oh, that's brilliant. By keeping the inner image and text interactions causal, they keep the attention matrix sparse enough to be computationally viable.
Exactly, while preserving the rich bidirectional context needed to actually understand a specific image frame.
Because in a traditional modular VLM, when the model tries to reason across multiple frames, it is comparing representations that have already been flattened and compressed by a frozen external encoder.
Yeah, you lose so much detail.
But in NEO-OFF, because of this unified attention mask, pixel word and pixel interactions are happening at the very earliest layers of the network.
They emerge from raw patch-level tokens instantly.
And that cross-image comparison is refined progressively throughout the deep layers of the LLM.
You are allowing the model to model precise, fine-grained visual differences and subtle temporal dynamics that a modular model's encoder simply throws away.
But you can't just build a radical encoder-free architecture, initialize the weights, and expect it to converge, right?
Definitely not. If you feed raw pixels directly into an LLM trained on text, you will completely obliterate its linguistic priors.
So how do they train it?
The authors detail a very progressive 3-stage training recipe required to bridge this modality gap. Stage 1 is the pre-training phase.
And what's the scale of that?
It utilizes roughly 20 million image-text pairs. The entire goal here is to align the newly formed visual tokens to the LLM's highly semantic representation space.
And this is where they introduce the pre-buffer mechanism, right?
Yes. Since they don't have a massive VIT doing the heavy lifting, the pre-buffer acts as an impedance matcher.
It's basically a lightweight bridge.
Usually just a few specialized layers. It's designed to project raw, geometric 32 by 32 pixel tokens into the high-dimensional manifold that the language model understands.
But without losing the spatial coordinate.
Exactly. And to protect the LLM's language capabilities, they strictly freeze the core language model in stage 1.
Oh, so what are they actually updating?
They only train the initial convolution patch embedding layer, this pre-buffer bridge, and the newly introduced QK parameters for the spatial attention heads.
Makes sense. So stage 1 is teaching the visual cortex to talk to the brain without frying the language center.
That's a great way to put it. Then stage 2 is mid-training, and this is where they really unlock the scale.
How many samples?
They introduce 60 million multimodal samples. They push the resolution way up to 4096 by 4096 images.
And what about video?
Video processing gets pushed up to 128 frames.
Wow. And do they unfreeze the model here?
Yes. Every single layer in the model is unfrozen and optimized in stage 2. They stretch the context window from 16K up to 36K tokens.
And what's particularly critical for anyone listening who is trying to replicate this is their data mixture ratio.
Oh, the ratio is fascinating.
They use roughly 2 parts text only, 4 parts image text, 1 part multi-image, and 1 part video.
2, 4, 1, 1.
Right. That ratio heavily weights image text alignment while maintaining enough pure text to prevent catastrophic forgetting of basic reasoning and linguistic structure.
And then stage 3 is supervised fine-tuning.
The polish phase.
Exactly. They use 6 million high-quality instruction samples spanning visual question answering, OCR, math, complex dialogue, and temporal reasoning.
So this is where the model learns to format its outputs and handle specific, complex human instructions end-to-end.
Exactly.
So to recap your training pipeline, stage 1 builds the neural bridge without frying the language center. Stage 2 is basically throwing them into an IMAX theater to build an infinite attention span.
Yes.
And stage 3 is sending them to grad school to answer specific questions.
That is exactly how it works. And the empirical results demonstrate exactly why this massive compute investment is justified.
Let's talk benchmarks.
On standard benchmarks, NEO significantly outperforms previous native VLMs like Fuyu and the EVE series.
But how does it hold up against the modular models?
It operates neck and neck with top-tier modular models, specifically QNAND 3VL and InternVL 3.5.
Even on the big evaluations.
Yep. Across extensive evaluations like MMMU, Video-O-Me, and Illusion Bench. Achieving parity with those modular giants without relying on an external visual encoder's legacy pre-training, I mean, that is a major milestone.
But the standout victory, and honestly the exact reason you probably forwarded this paper to us, is Spatial Intelligence, or SI.
Oh yeah, crushed it.
When tested on dedicated spatial benchmarks like VSI Bench, MindCube, and MSpatial, NEO didn't just outperform general-purpose modular models.
It actually outperformed actual spatial specialist models.
Right. Models like Cambrian S and GeoThinker. It absolutely dominates in low-level geometric perception and high-level spatiotemporal reasoning.
And the causality of that spatial intelligence victory points directly back to the architectural removal of the CLIP encoder.
Because it's not compressing the data.
Exactly. Because NEO doesn't compress spatial data into high-level semantic embeddings, it retains the fine-grained geometry and exact positional relations.
Did they actually prove that in the ablation studies?
They did, explicitly. They compared their lightweight pre-buffer mechanism against conventional visual encoders, randomly initializing both for a fair fight.
And what happened?
The native pre-buffer architecture consistently achieved superior performance on SI tasks.
Because of those early layer interactions?
Yeah, those early layer bidirectional pixel interactions allow rich spatial representations to form organically.
Rather than forcing the model to guess the geometry from a flattened semantic vector.
Exactly.
We do need to look at the limitations, though, because it's not a complete sweep across every single modality.
Right. No model is perfect.
There is a lingering performance gap on OCR-intensive and document-centric benchmarks when you compare it to a model like Qwen3VL.
Yeah, that's true. Tasks involving highly dense text perception, complex charts, and intricate document layouts still present a challenge for this native architecture.
Now, why is that?
It really comes down to the legacy data leverage inherent in the modular paradigm.
The pre-training data.
Exactly. Modular models benefit immensely from massive, specialized, OCR-oriented pre-training that has been baked into their specific visual encoders over years of iteration and, terabytes of document scans.
So Qwen3VL's vision encoder has incredibly strong priors for high-frequency textual artifacts.
Exactly. Whereas MEOF, on the other hand, is learning OCR basically from scratch through its raw pixel ingestion.
At this stage, it simply lacks the sheer volume of diverse, dense text-visual supervision required to match those specialized priors, which poses a massive question for the future of your model architectures. Is this gap purely a data scaling issue?
That is the million-dollar question.
If the next iteration of NEO includes 100 million high-quality document scans during Stage 2 mid-training, does the modular paradigm become completely obsolete?
It's highly likely.
Because if the only remaining advantage of the modular system is legacy pre-training data inside the vision encoder, that is a highly fleeting advantage.
The trajectory heavily suggests that the modular advantage is temporary, and that points to a fundamental paradigm shift.
It really does.
For years, the industry has treated vision, audio, and language as biologically separate modalities, requiring entirely separate processing units that we hack together via adapters.
Like bolting on aftermarket parts.
Right. But NEO demonstrates that multimodal intelligence can emerge intrinsically from a single, unified, monolithic network.
Instead of bolting on separate sensory modules to a language model, the future clearly points toward native neural substrates.
Models that process reality exactly like human perception does.
As one continuous, undivided stream of spatiotemporal data.
And the implications for AI hardware design are just staggering.
Truly. If we no longer need distinct chips, partition memory architectures, or complex PCIe bandwidth management to shuttle data between specialized vision encoders and language decoders, well, the efficiency gains at data center scale will redefine how we build inference hardware.
We're looking at a unified generalist architecture replacing a patched-together system of specialized experts.
You can check out the paper. from pixels to words, to dive into the exact parameter counts, hyperparameter configurations, and ablation tables for your own builds. Thanks for dropping this in our queue, and we'll catch you on the next analysis here on AI Paper Slap.